Here. So welcome everybody. So today I'm going to spend an hour on fluorescence. Some of this may be, let's say, very basic for some of you. Some of this may be advanced, but I hope I can sort of find a middle way so that it is something for most of you. You see. So first of all, just want to introduce you to where we are on the electromagnetic spectrum when it comes to fluorescence. So we are in between having ultraviolet rays and we have the visible light. And this is really the area that normally we talk about fluorescence. In principle, you could also go a bit into the infrared area, but normal instruments don't give any signal in this area at all. So in order to just sort of give you an idea about what type of molecules it is that you can see, I would like you just to give an example here. Let's say it's relatively simple from some, maybe it's very advanced for others, but these are what we can call pi bindings between two atoms in a molecule. So we can see here we have what we call the p binding here between two carbon atoms, and this means that you have a double bond is also what we sometimes call. And then you have your electrons will then between the two carbons will be shared so that binding these two carbons more tightly together. The opposite is if you have what we have here, the pi star, is when the electrons are not paired and they're actually pushing the two carbons apart. So if you draw up the molecular orbits between these two atoms, so this is carbon and oxygen here, it's a ketone, then you can sort of, all the dots here, these are the electrons, and all the lines here, they are the different orbitals, so between the two atoms. Now what is happening, and now if I draw this instead, in energy, then we have here on the right-hand side, you can sort of see relative energy intensity, and you can see that, yes, we have this anti-bonding P here being the one that is not populated, the one at the bottom which is not populated. We also have what we call an non-bonding sigma up here, but that is not going to be touched. So what is happening when we have something like fluorescence? Well, you will get a transformation from having, so what we see up here, you have from the p bonding into the anti-p, and when we actually see the emission, that's what we see down here. And it's actually, sorry, this is another alternative going up from the non-bonding. But I leave it at that just to note, so that you already have an idea that you need some double bonds before you can see any fluorescence. Now, if we're looking at the big picture of spectroscopy, we are in a small corner here called electron spectroscopy, and down, always quite often put it like below UV-Vis, because you can see it as a subpart of UV-Vis. You measure in the same wavelengths as UV-Vis, just a bit differently than what you normally do. And in the following slides, I would like to show you what is different. So what is it? What makes this a different method than most spectroscopic techniques? Well, if you talk about spectroscopy, you have a source here. This is typically could be a light source giving the light of the wavelengths that you're interested in looking at. Then you have your sample, and then you see how much of the light passes through your sample, and by that you get an idea of what your sample contains. Now, in fluorescence, it's different because we don't look at what is coming directly through the sample here. So we're not looking at what is happening on this side of the sample. If we did so, that would be regular UV-Vis spectroscopy. What we have here is a light source. This is typically a xenon lamp. I'm getting a bit back up to that. And that will then go in and hit the sample. If you have fluorophores there, they will be excited. If you have absorbers there, they will also then absorb some of the light. So things will be excited here. And then if you have fluorophores, they will also emit some light that we can detect and record on a detector. So if you go a bit back here, so absorption, that will happen for many different molecules, but only the fluorophores are the ones that we will be able to spot by fluorescence. So a typical excitation spectrum, this is for tryptophan, can be seen here, where we can see that the intensity increases in the beginning, and then it just decreases down to 0. So meaning that it doesn't give a signal in the whole spectrum of UVVs, let's say, that we have here, but only in the beginning. And this is an electron transition that is happening in the beginning here. So you're going from the ground state. Now, what we're really measuring, we're not really measuring the excitation. That we get like as a secondary thing when we do the fluorescence. What we're actually measuring is the emission. So we are measuring the light that the fluorophores are capable of emitting out, and that we can read off again, so we can detect. Now, most of the energy that is absorbed by a sample will not be re-emitted like we have in fluorescence, but it will be due to diffusion. It will just go back to the ground state, and you can't really detect these energy changes. With fluorophores, you can detect this energy difference. So this is a typical tryptophan emission, and we'll also get back to how this looks. Most importantly, if you now plot both of them on the same figure, so you have in blue here, you have the excitation profile, and in the red, you have your emission profile. The difference between the maxima of these two spectrum, that's called the Stokes shift. So you can see that it goes up in wavelength, and that means that it goes down in energy. So it's a lower energy that you get out. Now, you could either measure the emission profile, as we see up in the red, or you can measure the excitation profile in blue. But you could also measure both of them at the same time, meaning that now we are measuring several emission wavelengths, the several emission spectrum, as a function of the excitation. And then we can get what we call an excitation emission matrix. Also going to get a bit back to that, but not very much. This is how we, in our section, prefer to look at fluorescence. Let's just go a bit back now to fluorescence and what is actually happening. So you can say here, these are again back to the orbitals that we were looking at in the beginning. So this is the ground state of a bond. And now we can be excited, so the electrons can be excited, go either to the S1, which is the first excited state, or the second excited state. You can even go further, but that's not normally what you can look at when you do your fluorescence. All these lines in between here, so all these other black lines here, they are what we call vibrational states. And this is what you normally would start looking at when you do, for example, IR or Raman spectroscopy. But then you would normally looking at down here at this level and not between the two. And what I've stated up here is that this excitation, it happens, well, it's not instantaneously, but it takes it's in a pentosecond scale. So in 10 in power of minus 15 seconds, this is what happens to a fluorophore when light hits it. Then once the electron is up here, it will go through internal conversion back to the lowest vibrational state of the S1. That's what you see here in the wiggly arrows. And you can also see that that happens also fairly fast. Now, what we are measuring with fluorescence, that's going from this lowest S1 and back down to the ground state. And as you can see here from the two arrows, it doesn't necessarily go back to the lowest vibrational level, but it goes down to a vibrational level of the S0. And this emission, well, that happens in the nanosecond scale. And the nice thing is that this is actually possible to start measuring in systems today. Bit more complex here, because I just want to indicate also that we have something related, which is phosphorescence, and that's what I've sort of shown here in the green on the right-hand side. This is not something that is happening very often, and it's not all systems that can show phosphorescence. But at least I remember for when I was small, I had this nice small Playmobil figure. Unfortunately, I lost it during the ages. But when I shone light on it, I could have it under my duvet and it would be nice and shiny for a long time. That's phosphorescence. And nowadays, I know that at least in the room I'm sitting in right now, I have some nice stars up in the ceiling, which is also phosphorescence, showing exactly the same, emitting light a long time after it has been light on it. And if you can see here, the time scale is also very different. Here we're talking about milliseconds. And this can be even longer. It can be minutes as well, like you have maybe experienced. This is also to show why some, to indicate at least why some molecules do show fluorescence and others not. If you look here on the left-hand side, this is a typical of a compound that does not show any fluorescence. You can see that we here have different, all these curves here, they are different states of a bond. And if you see that these are the energy, the horizontal lines, these are the energy levels it can have. And you can see here that, well, I can transfer from all these energy levels, just going from one step to the next, all the way down if I go to the upper ones. So here, there's no need for the molecule to actually emit light again. It can go through like very, very small increments of energy, releasing, until it's all very relaxed, and we can't see this energy difference. And this will happen very fast as well. Now, in a fluorophore, you have what you have on the right-hand side, and here you see that there is no overlap between these two levels of energy like you have on the left-hand side here. So the energy goes up here, by the way. And then here you will have fluorescence, and typically happening in the sub-nanosecond to can be up to several tenths of nanoseconds. An example of that can be shown here, where you have two very similar molecules. You have phenolphthalein on the left-hand side and fluorescein on the right-hand side. The only difference is that on fluorescein, you have an oxygen that is binding the two uppermost rings here together. This makes this molecule, the fluorescein, is not as flexible as the phenolphthalein. And fluorescein is one of the most probably strongest fluorophores that there exist, and phenolphthalein is not fluorescent because it can give away the excited state, so it can relax again just by rotating its way down in energy. So some dictionary here, just to sort of summarize the first part. We talk about luminescence. I haven't really said about that, but luminescence includes both fluorescence and phosphorescence, so it's both of the two. So fluorescence, and that's going from an excited single state and back to the ground state. And it normally happens, as I stated, in the nanosecond scale. Phosphorescence, then you have something called excited triplet state, went very fast past that because that's not the main goal of this talk today. That's rather slow, and as I said, many minutes can be up to. Now a bit more details. I haven't talked so much about fluorophores. Now, a lot of people doing fluorescence out there, they are adding fluorescent probes to the system, and then they're monitoring how these probes are changing. And these probes are typically something that you attach that binds specifically to some part of a molecule, or it will bind to when there's a binding of a certain type that you're interested in, then this fluorophore will also be active. We, in our section, we're not really working on extrinsic fluorescence. I never worked with one. Once I have, but only by some students. I'm mainly interested in the intrinsic fluorescence, which is also what some people term the autofluorescence. And that's when you are looking at the fluorescence of the system under investigation. Stokes shifts, that's the difference between the excitation and emission maxima of one fluorophore. Then you have something called quantum yield, and that goes into how much fluorescence does a specific molecule give. And that is very dependent of the molecule, as it is with all spectroscopic techniques, but also like you have with all the chromatography as well, there's different affinity to the system. So how much signal you have. So how does this instrument look like? This is one simple way of looking at it. I think I will skip that because I want to go into a more detailed look. So you can see that an instrument, and this is just a typical instrument, you have one side which is an excitation, then you have your sample, and then you have emission on the other side. And this is this signal here, so that what comes to this red detector, that's what the signal that you're going to read off at the computer in the end of the day. but it does contain a lot of other details as well. So you have the light source, xenon lamp, getting very shortly back to that. You have a grating, which is a mirror that is turning slowly, and all depending on the angle of this mirror, that is the light that is then going to go further into the instrument through a beam splitter, and then that light is going to hit the sample. So this is a very, very specific wavelength that depends on the grating. Now, in the beam splitter, some part of the light will then also travel to a reference detector. In some instruments, this is a signal that has been used actively, meaning that the signal that you measure here is corrected for whatever is seen here. In others, it is more of internal standardization in the instrument that you as a user will never see, but that is recorded anyhow, so that the vendor can know, okay, something is happening with a light source. If this starts the signal down here, that this detector starts going down, you know that something is happening to the light source. Then you have your sample, and this is in a 90-degree configuration, meaning that the light comes in here, and then you're measuring 90 degrees angle onto this sample. Then you have some mirrors, a new grating, because then this grating will then decide what wavelengths you are actually measuring in your detector here. These slits, they are something that you can adjust depending on how much light you want to get through, how precise you want to be. Not going to talk much about those either. Going back to the light source, now what would be really perfect would be if you had the light source that would be uniform throughout all the wavelengths that you want to measure. This does not happen. A xenon lamp is one of the better ones with the most stable across different wavelengths. But as you can see here as well, this goes from 200 nanometers on the left-hand side to 1,000 nanometers on the right-hand side, and certainly is quite spiky. Now, of course, this doesn't matter so much if you correct your spectra nicely when you're measuring, because then you can always, you know that, for example, this wavelength here at 220 nanometers is way more intense. The light is way more intense than what you have here at 400 nanometers. And of course, you can correct for this because this is how the light is looking. This is how the light bulb is looking. So this is a profile of the light. Now on the detector side, quite often you are using what we call the photomultiplier tube. That's PMT, and it's photomultiplier tube here. And what that does, that increases the signal from your photon. So from the photons that is sent from your sample, you will then try to increase this. And the technique here is then that you have your photon that hits a metal plate, and that will release one electron. Now this electron will hit one dynode, and all depending on how much voltage you put between these dinodes. So you see you have several of them here. That's all these black semicircles. You will then start increasing the number of electrons that are released from one. So if one electron hits here, you can see that two are released, and then from this one, two are released per two here, and so on. So at the end of the day, you're measuring what is happening here at the end, at the anode. And now you can probably also get an idea that, of course, all the higher voltage that you put in between here, the more signal you will get at the end. But for those of you that have been working a bit with electronics, you probably have an idea as well that the noise is also increasing here. So that even though you get a higher signal, you also get a higher noise. So you have to play a bit with what voltage you can use. Now let's go a bit back to the molecular structure, because it is important to have an idea of what molecules is it that you can look at when you're doing fluorescence. So generally you have aromatic compounds. Those are very good fluorophores in general. Conjugated molecules is also good to look at. And then you have electron donating or withdrawing groups on these aromatic rings, and then can certainly affect fluorescence. These are just some fluorophores in food. And what is, of course, what many people are interested in these days, that's these proteins here. And now we don't really see proteins per se by fluorescence, but what we're looking at are the aromatic amino acids, typically tryptophan and tyrosine. Phenylaniline is by itself fluorescent, but it is so the quantum yield of phenylanilene is so small that you will not be able to see it. Furthermore, there's an energy transfer from your phenylanilene to either of the two others. Now that said, also the tyrosine is way smaller than the tryptophan. So what you really are looking at when you are looking at your, most often when you're looking at your proteins, well, it's this guy here. The nice thing is that it's very sensitive. I can say that it's nice. It's very sensitive to its environment, and I will look a bit back to that very shortly. What we also can do with regards to proteins is the modifications, being that Maillard reactions or being oxidation. And we are working heavily on that. There's also a lot of literature already on some of these. And some of them are accurate and some of them are not. Not go so much back to that. This is just a landscape with a lot of the fluorophores. So you can see the different ones here. Not go really in detail here. Then, of course, concentration will also affect the fluorescence. Now, this is a Lambert-Beer's law for fluorescence. Yeah, it's a bit long and tedious, so I made a, let's say, a short version of the same equation. So we have here your fluorescence signal. That's the IF here. Well, that's a sum of all your fluorophores. So that's the I's here. These are the different fluorophores. These are all constants depending on the fluorophore, and this is the concentration of the fluorophore. So in an ideal system, it will follow this rather simple equation, let's say. But you do have a lot of things that will affect your fluorescence. You have inner filter effect, which happens when you have too high concentrations. And that then you can divide this into two types of inner filter effect. You have what you say is primary, and that's here when you say that when you come, so when the light is coming into the system, so when the light is coming here, well, some of the light will not be able to reach the fluorophore if we indicate that as the darker green here in the middle. On the way, it will be absorbed by any other molecule on its way, and this is called the inner filter effect, because not all the molecules that you have in the system will have the same probability of being excited. Now, in addition, you have what we call the secondary inner filter effect. That's what's happening out here. So when the light travels out again, so here you have this one has been excited and it emits light going out here, but before the emitted light actually is released from the cuvette, some of it can hit other molecules and will be reabsorbed, and thus the light that coming out is way less than what you had in the beginning, what it should actually have been in a perfect ideal condition. How to deal with this? Well, one way to solve it is to use a micro cuvette. A micro cuvette just means that you have a way narrower path length in either one or in both directions. Here you can see that this is only smaller in the excitation direction. The emission here is as big as it was. Now, depending, of course, where if your biggest inner filter effect is primary, then this solution would work fine. If your main inner filter effect was in the other direction, well, then you could probably just, flip your cuvette the other direction and you could solve it by that. But if you have a problem in both, then you either need to go in a micro cuvette that is shorter in both directions, or you need to do something completely different when you do your measurements. One such solution is using front face geometry. Now that means that instead of measuring the regular 90 degrees, so meaning that if I just draw in the bottom here, so normally you will have your sample here, you will have your light coming in and you're measuring what comes out. This is called the 90-degree setup, and this is what is normally done. You can instead use what we have here, a front face measurement. Now what is happening here is that you'll only actually then measure part of your cuvette. And this is important to know because you're mainly measuring the surface of your sample here. Now, if you have a very homogeneous sample, that doesn't really matter because this will be representative of your sample. If it's very heterogeneous sample, you are starting to get a bit of a problem with regards to something called sampling. I'm not going to get into that though. Now, if maybe you can see my screen, I can't, it's nicely turned off. Sorry about that. I guess you can see. Sorry. Okay, now we are back again. Can you see the screen?
Yes, fine.
Move this one. So normally it is to correct, it's possible to correct for these inner filter effects by measuring UV-Vis. And then you can use the equation that you have down here to do the correction. What this states is that this is what you have measured. And then you need to use the absorbance that you have measured with UV-Vis in order to do the correction. And this UV-Vis you have to then measure with the same cuvette as you are measuring your fluorescence with. Now, this correction was originally founded based on a regular geometry, meaning 90 degrees system. If you're doing front face, you're not doing 90 degrees, of course. This small number here, 0.5, indicates sort of that what you're measuring means that you're going half direction in both, you're going halfway through in both directions of your cuvette. So you're going half a centimeters in and you're going half a centimeter out again. Let me just try to draw that here. So if you have your sample, well, you go halfway in, that's your that's the first half, and then you travel halfway out. So this is the first half, this is the second half. And of course, if you have a very dense sample, you probably won't see this much of your sample. So what Marta did together with Marianne and me some time ago was to play around with this number here. I'm not going to go into detail here because this is a rather dense figure, let's say. But if you can see here at the bottom, it says 0.5 here in the red areas. So this is what is normally done. And the higher these graphs are, the better the solutions. And you can see that it's not always the half that gives the best options. It gives the best results at the end of the day. So this just points towards that this one here, it's not really the truth, okay? It's been used by a lot of people extensively, doesn't necessarily hold when you start doing your actual analysis. Another thing that is very much affecting fluorescence, which is also affecting many other spectroscopic techniques, are environment that is being measured in. Now, if you're looking at tryptophan, it will be very much influenced on what type of solvents you're using. This is just showing two types of solvents here. So you have your water here in blue, and then you have the hexane here in the red. And this is just because how tryptophan then will be influenced by, it will be actually stabilized by one of them, right? And furthermore, it is also very much influenced by the pH. The change in pH will also change the intensity that you have in your fluorescence signal. And what you see here is that this is tryptophan as a function of pH, giving you a very low signal in the beginning of pH 3. And if you go very high up in your pH, well, you will also get a higher intensity in the fluorescence. Of course, this figure is not always, doesn't always look like this for all fluorophores. This is just one example. It's just showing that it is sensitive to pH. What has been done quite often in biotech is to use the sensitivity of the tryptophan, as I just mentioned a bit earlier. So the nice thing with tryptophan is that it is changing the signal all depending if you have a folded protein or an unfolded protein, meaning that if your tryptophan is buried, it will give you one signal, and if the tryptophan is solvent exposed, it gives you a different signal. Now, if you look at the ratio between the two, that's what we have up here. So up on the top here, we have the ratio between the two. And then this is with increasing temperature. We can see that we have then a different profile of how the temperature affects the fluorescence signal, or this ratio rather. Now this has been measured at serum pH values, and you can see how pH will then change how this profile behaves. Now this has to do with then what we can see here in the blue at pH 5. You can see that you start getting an unfolding of the protein rather early on. If you increase the pH value, you will prolong this period of a stable protein. Quite often this data is looked into in a derivative like we have at the bottom, but I'm not going to go further into that. It's just to show what you can do. Another thing that is done quite a lot in biotech is to look at denaturants instead. So this is guanidine and hydrochloric acid. And all depending on how much you're adding, and so here you have from concentration of 0 molar and up to up to 5.5, you can see that the emission spectrum changes drastically, all depending on how much of these denaturants that you're adding. And again, you can spot then that from being on, well, there are some outliers here, these in the bottom here, something went wrong. Well, not going to go into detail with that, but if you're looking here, you can see that you have here a nice folded protein, and in purple here, this is an unfolded protein. So it has opened up completely. Then we have something called quenching, which can also affect fluorescence. And that's a process that decreases your intensity. And that's also divided into two, something called dynamic quenching and something called static quenching. When we have dynamic quenching, it means that your fluorophore will actually hit another molecule that will then dissipate this energy. So you will see a decrease in your fluorescence signal. And the static is then it actually is forming a complex together with the fluorophore, and this complex will not emit any fluorescence. Now, the nice thing, when you do steady state fluorescence, you will not be able to see the difference between these two, but you can also use this actively in order to figure out what you have in your system. If you know of a specific quencher that will quench one type of your signal, well, you can keep on adding it and looking at how much of a signal do you have. And then you can know, then you have an idea of how much you have of what you're interested in. And if you're not sure if you're looking at static quenching versus dynamic, it's possible to look at time decay fluorescence, and then you actually can get an idea of it is either or, because that can separate these two. Another thing that is happening is a non-radiative energy transfer. This is what I mentioned in the beginning here with proteins, or earlier today with proteins, that you have energy being transferred from phenylalanine to tyrosine or tryptophan, or from tyrosine and up to tryptophan. So what we can see here is that you have, if I can get a bit of a pointer here. So here you have one molecule, this could be your tyrosine. It will then absorb light at some specific wavelengths in a certain profile. And then it will be able to then emit light, and that's this blue peak here. Now, in the same solution, you also have, or even close to this fluorophore, you also have another amino acid like the tryptophan. So the tryptophan has a different shape on its excitation profile, and it will start being able to absorb some of this light that is emitted by the tyrosine. Now, this will then be able to then emit light at a lot higher wavelength. Now, what you're observing in your system and in the measurement is you observe that something is being absorbed at this wavelength, and it's emitted at this wavelength. Now, the Stokes shift going from molecule 1 to molecule 2 here, you don't know this, of course, because you can't see what is happening in the middle here. You just notice that this is very high. It is too high for a molecule to be able to be stable with this large energy difference. So you will have an idea that something has happened. You just don't know exactly what. And this, of course, can be problematic. But again, you can also use this to your advantage when you're measuring. Not going to get back. This is just a bit showing what is happening. So just run quickly across that. We also have something called Raman and Rayleigh scattering. Two other issues. These are not so big of a problem as all the other ones that I have mentioned. These can be handled fairly nicely. So if we're talking about scattering, we have here the Rayleigh scattering, where the emission equals the excitation. And this is it's highly affected by particle size. And for those of you that have been working with dynamic light scattering or static light scattering, it's exactly this line that you're interested in and how broad it is. Now, the small fellow down here, it's not so easy to see when you have a fluorophore in the middle. This is the Raman signal, and this is also what you're measuring when you're doing Raman spectroscopy. And for those of you that have been working with Raman spectroscopy, you may have thought of fluorescence as being a nuisance to your Raman spectra. Well, in fluorescence, you would say the opposite, that the Raman can be a nuisance to the fluorescence. So it's a bit love-hate relationship, let's say. Now, on the edge here, you have something I've noted here as being the second order Rayleigh, where the scattering equals twice the excitation wavelength. It should be noted that this here is actually not related to fluorescence per se. This is instrument dependent. Now, most instruments that are out there, fluorescence instruments that are out there, they are on the, let's say, cheaper prices, meaning that you only have one monochromator on the detector side, and then you will get this as an artifact. This is an artifact of the instrumental setup, and not because of fluorescence itself, but it will happen at emission equals twice the excitation. It also means that the signal you have here will come as a copy outside of your second order Rayleigh scatter. It's not any new information, it's just a copy. Lower intensity, way lower intensity. Here's just to show, again, the same. This is just a water sample, so you have a nice Raman signal here. And if you notice here that the distance between the Rayleigh and the Raman is longer in wavelength in the top than at the bottom. But the energy difference between the two is constant. And this is 3,600 reciprocal centimeters in difference. And if you know Raman spectroscopy, you know that very well that you have a water peak there if you measure with the correct laser. So how to measure fluorescence? Well, you can measure your emission as a function of excitation. You can measure excitation. You can also do something called polarization and time decay. I've only been talking about these two up to now. Now I will just briefly talk about these two next ones. I will not go into microscopy, but that is also something that people are using fluorescence for heavily. When it comes to polarization, what is interesting here is that normally you will excite with a polarized light, and that means that it's not really guided in a specific direction. If you don't know what polarization is or how it really affects things, if you ever have tried to take some good sunglasses with a polarized filter on them, you put it in front of your computer screen and you start rotating your glasses, you will see that the light, what you see through your lenses will change. And this is polarization. It's exactly because you're looking at the polarized light through your sunglasses. You can use this actively in fluorescence spectroscopy. And what really can tell you something about is the size of the fluorophore and the viscosity of the solvent. Because what you can measure is then the difference in what we call here, this is the vertical polarized light and vertical and horizontal polarized light in the emission mode. In the excitation, you will only work on the vertical. So that is fixed, and then you will swap then this grating here. So this is your polarization lens, all according to how you want to polarize your light. Time decay, something we have started playing with now recently, let's say. We got it back in, now Rasmus must correct me, but I think it's now 3-4 years ago since we started playing with this. What you can see here on the x-axis, it says channels up here, but if you look all the way at the bottom, it's probably more interesting. You see that you have time in nanosecond scale. So you can see that, okay, it doesn't start at 0, no, and that's because it's difficult to know, it's difficult to align the instrument so that you get exactly 0 in the beginning. So you get an axis that starts from somewhere. It's not really crucial because you can always, when you get the signal, which is the blue line here, you can always figure out later on when 0 is. So that's not a big deal. Now, the big challenge with regards to this time decay curves is that what you're really interested in is the slope of this black line here. And that's the time decay. Now you can, if you notice, it's a logarithmic scale on the y-axis here. However, this time decay is influenced by this red fellow here. Now, the red fellow is called the instrument response function, and it is dependent on the instrument and even more so the light source that you're using. Not going more into details, but if you see here, especially here in the top part here, you can see that it doesn't look as nice and linear as it does in the, down at the right-hand side, but here again, it's also more noise. So a summary of what I've been talking about so far. So you can measure the fluorescence as a function of excitation, emission, those that have gone in more detail. You can also measure polarization, and you can also doing time decays. The specificity is medium, and that's because these peaks are quite broad. I haven't really shown that one landscape in the beginning where you sort of have an idea of what different fluorophores you could look at. A drawback, but also strength, only few molecules are fluorescent. It's a drawback because you can't look at any system when it comes to fluorescence. The good thing is that if you know that you have a fluorophore, it could very well be that it's not so much else that is disturbing your signal. Intensity is proportional to concentration. This is the ideal case, and as I also have sort of indicated, you can have problems here if you have too high concentrations. It's a very high sensitivity. We talked about that, but people are claiming that they can go down to PPT levels. I haven't seen that myself, but I have seen down to ppb. That is, if you have a strong fluorophore, you can certainly go down to ppb levels. It is very sensitive to a lot of things, but that can also be used actively when you do your measurements. And that's the beauty, let's say, if you know what you're doing to your system, you can also use this to your advantage. And it's also what I'm stating here. So, and then you also have scattering, inner filter effects, radiative energy transfers, and you have quenching. So all these in the two last ones, not the very last, but these two, of course, they can both be a disadvantage, but also an advantage. So a bit on why. High sensitivity. It's a medium specificity, but you can increase that by increasing the number of modes that you're measuring. It's non-destructive, and you can also use it for online analysis. It's not very much used for this, though. There are several relevant fluorophores in food, and you can then use it actively to investigate changes in systems. Here are just some ways to measure fluorescence. You can do one excitation emission pair. This is not so much done anymore because people have realized that that is not exact enough. And you can do an excitation or an emission spectra. Here you are getting more information at least, and you're getting a better signal. And then you have two different ways of doing it three-dimensional. One is excitation emission matrices, and the other one being synchronous fluorescence. Excitation emission matrix means that you're measuring the emission spectrum at several excitation wavelengths. So that's sort of just an expansion of what you have up here. Synchronous fluorescence is a bit different. And that means that now you are measuring the emission at a certain offset from the excitation. And then you actually do an excitation scan, and then you get that offset on your emission spectrum. And then you can change this delta to be different. And then thus you will get a three-dimensional landscape with synchronous fluorescence. The problematic is that the output here in synchronous fluorescence is not bilinear in nature, as we would call it, as the excitation emission matrices. But this is more data technical, and it could very well be that you will be better off doing synchronous fluorescence, because the nice thing is that you travel on the diagonal in the landscape instead of in the excitation emission, where you go horizontal, let's say. Then you can do time decay fluorescence, and you can also do anisotropy, and all of these can be combined. So just two examples here at the end. And this one was actually added rather late today before this talk, because we had just had a meeting in one of the projects that I'm part of. And then I started thinking of an old work that I did during my PhD, where we look at what we call the second order advantage. Now, I don't think I will say too much about the second order advantage. I think more focus on on the system here. So we have a set of 2 fluorophores. So we can see here the excitation in the bottom in blue and green. And then we have the corresponding emission profile up here on top. Now let's say that I have these 2 compounds in my calibration system. And these are the 2 compounds that I'm interested in investigating in my future samples as well. The problem though is in my future samples that are looking on the right-hand side, now you can see that all of a sudden there are more things happening. You can see here that this cyan here, well, that's the same as the blue one. And the purple one, well, that's the same as the green one here. But there are also 2 other things happening, and these are called interference. So I could attack this problem by making, for those of you that are familiar with multivariate data analysis, I can make a partial least squares regression on these data and trying to predict the new samples. I could also look at it from a multi-way perspective and doing something called ParaFAC, and I will not really talk about what the difference is here. But the nice thing with ParaFAC is that then I will use this second order advantage. If I do partial least squares, I will not. So if I do ParaFAC instead on this system, and then I make a prediction of my 2, the catechol and hydroquinone that I have in here my calibration samples, and we get 2 very different results. Now, if we look here on the left-hand side, this is what we call an actual versus predicted plot. The red dots, well, that's from the ParaFAC approach. The blue dots here, well, that's if you do the partial least squares approach. And at least back in the days, I used to refer to this as being the accuracy of, you know, a good football player passing the ball and then a Norwegian football player passing the ball. The accuracy is kind of different, you can say. And if you look at the RMSCP value, you certainly see that the error in the blue here in the partial least squares is way higher than what you have for your ParaFAC. So, and this is the second order advantage, why it is a good idea to measure excitation emission matrices and apply the correct mathematics afterwards. Finally, before I stop and leave it for questions, I want to show some data that was made by master students some years back. We will looked at the protein in different salt solutions and pH values. And this is just to get an idea of how we can study proteins with fluorescence. Just very briefly, this is the Hofmeister series. It's an old series that was published in the 1880s, as far as I remember, where you say that, okay, different anions and cations, they have different effect on proteins per se. Some are cosmotropic and chaotropic. Won't go very much into that because that's not really the aim of this talk. Anyway, we had beta-lactoglobulin. That's very much food related, at least. And then we use different types of salts, and you say buffer, it means that there is no salt added, and then measured at different pH values. The nice thing, and then of course we measured fluorescence on these, and by applying this ParaFAC, as I have been showing very slightly, we get this result. So here we have the excitations on top, and we have the emission profiles on the bottom. The nice thing now, you can see that the red and the blue here up in the excitation, they are very similar. And that they should be, because these are the 2 tryptophans. So this is the blue one here, that I know from looking down here. The blue one here is the solvent exposed, the red being the buried tryptophan. And you can see that there's very little difference in them in the excitation profile. If you look at the emission profile, there's quite a large difference between these 2. And this is what we can look at if we want to look at the stability of proteins. So we can see that there will be a change in your fluorescence from more on the buried side to the more solvent exposed, well, they know that it has started to unfold. What came as a bit of surprise, I can say more, is that we were also able to see this yellow guy here. Now, in most, if you're looking at beta-lactoglobulin, you will not be capable of seeing tyrosine because the amount of tryptophan is so large that the tyrosine is not visible. But here you can see this is tyrosine nicely being deconvoluted here in the excitation and also in the emission mode, nicely showing a maximum of about 304 nanometers. This is super, very nice. And of course, we can then look at how the different samples affect the different fluorophores. And you see that there are 3 dots here for each of the salts, and these are the 3 different pH values. Please note that for magnesium chloride, there was a problem with one of the pHs where we just got it was just started to aggregate immediately. So that's why there's only 2 dots here. It's just to show what fluorescence can be used for. So that's all for me for now. There's time for questions. Just the last slide here. Who we are giving these seminars, and please contact us if you want to know more.
Thank you very much, Osman.